Welcome back to the next lecture in Module 4 on specification and verification of code. My name is Rustan Leino. What we're going to look at today is invariants. So in this lecture, I will be talking about loop invariants, and that will be a stepping stone towards the more advanced examples that we will use in the next two lectures. An invariant in a computer system is something that you use all the time to reason about the system. It's a condition that holds at every point of execution, maybe at certain points of the execution, but it's a condition that we think of as holding in steady states of the system. So you prove everything from invariants, including absence of deadlocks, crash freeness, things like that, memory safety, functional correctness. They tend to be proved from invariants, data structure invariants, monitor invariants, and in these lectures, loop invariants. So for loop, the loop invariant is a condition that holds at the very top of every loop iteration. So it doesn't mean that it holds at all times during the program execution, but the loop invariant holds at the very top of each iteration. That's typical of invariants. Invariants are often falsified for short periods of time, and just exactly when those periods of time are depends on what kind of invariant it is, and it gets tricky in the reasoning depending on where those might be. But for loop invariants, it's pretty straightforward. They hold at the top of every loop iteration. So let's take a look. Let me just remind you that we're using Daphne as the vehicle to show these things. Daphne is a programming language that supports the sorts of specification constructs that we're talking about, and it has a verifier. And if you don't already have Daphne, you can run it on in your browser at riseforfun.com/Daphne, or better yet, install it on your machine on the platform of your choice. All right, here we go. So here are loop invariants. In this lecture, I will make use of a favorite little computer program, which is the one that computes Fibonacci numbers. So to begin with, I will write a function that specifies what Fibonacci numbers are. And this in Daphne will be a function. So a function is different from a method in that a method has code in it, it has assignments, it could have loops, it could have side effects in the heap and things like that. A function is a mathematical function. That is, it always returns the same value given the same inputs. It always terminates and things like that. It can never change the state of the program. So for these lectures, I'm just going to use functions as part of a specification, but you can also program with functions, of course. So the Fibonacci function is going to take an integer as an input and return an integer. Now, I could write some specification about this integer to say that it's going to be at least 0. But as it turns out, in Daphne, you could also write the type nat, which is a subset of the integers, and there are, in general, subset types. So here I will make use of that, so I don't have to write a separate precondition. It will just follow from the type that it is a non-negative integer. Well, in fact, let's also return a nat for the Fibonacci. Okay, so what is it then? So the body of a function is just going to be an expression. So there's no code in here. So don't be confused by the curly braces. There's no code. It's just an expression that sits inside the body of a function. And that I will write as using the ternary operator. So I will say if n is less than 2, then just return it. Else return the Fibonacci of the two previous Fibonacci numbers. So this is the standard Fibonacci function that we know and love, and it's simple to look at for this function. But if you try to execute this function, as you know, the performance is going to be spectacularly bad. So that's not what we want. But this just gives us a chance to talk about a program that will compute it, and in particular about loop invariants. So now I will write a method that is going to compute the Fibonacci, and I'll call it computeFib. It will also take an integer, a natural number, as an input, and it will return a number that is going to be the Fibonacci. So I said that in words, and I will now write that in a specification. I will say that the post condition is this method ensures that x is going to be equal to the Fibonacci of n. So note what I've done here. I've used the function, which is, as we said, spectacularly bad if you try to, I mean in performance if you try to execute it, but that's okay. It has a simple mathematical meaning, and that's the meaning that we put in the postcondition. The postcondition, there are some systems that evaluate postconditions and preconditions at runtime. Daphne is not one of those. It can be a tremendous help to check pre and post conditions at runtime as well, if you don't have the means to do the formal verification to check it at compile time, as we're doing here, checking it statically. But in Daphne, post conditions and preconditions are erased by the compiler. They're never checked in the actual, they're never present in the actual executable code. So I should feel free to write an inefficient post condition, if you will. That is a post condition that has a clear meaning, but we wouldn't actually want to execute it. Okay, how are we going to write this program? Well, what we're going to do is we're going to make use of a loop. And let me start by writing that loop in the way that you would be accustomed to doing it. So I will introduce a loop index. I will set it to 0, and the loop is going to continue as long as I is less than n. Now, we can fill in this loop, and of course we're going to fill in the loop body really shortly. But something that you have to think about when you reason about the loop is that the loop could have any number of execution sequences. In this case, depending on what n is, we'd like this loop to iterate n times, and that means that in general we would have to think of an infinitely large number of execution paths, and that's too much for our finite heads to consider. That's why we introduced invariant. So the invariant is going to say something that holds at the very top of every loop iteration. And that means that we can just reason about one loop iteration at a time. That is, we can just think of a general loop iteration and reason about that and make sure that it maintains the invariant. Very much like in mathematics, that we have an inductive hypothesis that we check, so we can prove a property for all values of something. So what is this invariant going to be? Well, typically you write one invariant about every variable, everything that could change in the loop. And I will write that here. I'll place the invariant just inside the loop here. And I will say that it's true that at all times I is less than or equal to n. So this is important. In fact, actually, let me write the other one too, because I think it looks nice to say that I is between 0 and n. And you can see in Daphne, you can chain the inequalities like this, which happens very often in specifications and looks nice. Turns out that the lower bound here, the tool will actually infer for us in this example, so we don't strictly need it, but it looks nice to see the invariant and see in front of you that I lies somewhere between 0 and n inclusive. Okay, so this is a condition that holds at every loop with every loop iteration. And what I mean by that is that it holds here, that is before the loop guard has executed. And that's important because we want the loop invariant to also be known to hold just after the loop. Some people think maybe loop invariant should hold just only if the guard, as long as the guard holds, but then that would not give us any leverage in proving things after the loop. So that's not how systems work. A loop invariant holds just before the loop guard, and that's true in Daphne as well. So don't be confused by the fact that the invariance is actually declared just after the loop guard, which is a little bit unfortunate, but it's supposed to hold here just before the loop guard. That means that even on the very last iteration where the loop guard is going to be false, the invariant is also going to hold. So again, I'm saying that it holds at the very top of every loop iteration, and what I mean by that is that it holds just before the loop guard is evaluated. Okay, so this is one loop invariant, and you can see that this loop invariant is kind of like a specification of the loop. If we can make this loop invariant hold with every iteration, then if this loop will ever terminate, it will terminate if we ever get to the very top of the loop and we find that I is not less than n. That is, if I is at least n, then this loop will terminate. Well, if I is at least n, and the loop invariant still holds. The loop invariant tells us that I is at most n. That means that on the other side of the loop, we can conclude that I is exactly equal to n. So note what is also quite typical, that when you have a loop bound like this, that the guard tends to be with a strict inequality, because we continue the loop as long as we haven't reached that limit yet. But the loop invariant includes that limit. So it includes the end just as well, because again, it needs to hold at the very top of every loop iteration. So it needs to hold even when we're going to find the loop guard to be false. Okay, that was many words about this one seemingly simple loop invariant. And this is the kind of loop invariant that once you get started writing programs, you kind of just write it automatically. You say while, and then you immediately say invariant, and you know what this range of the bound variables are going to be. Okay, let me write the loop body itself. So the loop body itself is going to, no surprise, increment I by 1. But by the way, before I did that, you can see that the verifier actually complains here that it cannot prove termination, and of course we need to increment the loop variable, the bound variable here, if we should stand a hope of terminating the loop. Okay, so while this is not enough, of course it's not enough. All we've done is we have a loop that increments I. We need to somehow compute x to be the Fibonacci of n. So what we would like is, as a partial solution to this, is that x at every time through the loop is equal to the Fibonacci of I. Because if we can make sure that x is always the Fibonacci of I, then when the loop terminates and, as we just reasoned, I is equal to n, then x is going to be the Fibonacci of n, and that's exactly what the postcondition is. You can see that Daphne no longer complains right now about the postcondition, because if we can maintain this invariant, then the postcondition will hold. So that's a good sign that we are going in the right direction of this for this program. Okay, how are we going to maintain this loop invariant? Well, we certainly need to initialize x initially. That's something we have not done yet. So what should x be initially? It should be something that makes this invariant hold. So I is initialized to 0, so that says that initially, just as we start the loop, x should be equal to the Fibonacci of 0. And if we go up to the definition of Fibonacci, we see that that means that x should also be set to 0. Okay, but this program, to maintain x being the Fibonacci of I, is going to be difficult, because we can then either try to call this function or compute the Fibonacci in some other way. And the way, which I'm sure you've already thought of, is that the way that we're going to compute this is we're going to keep track of 2 consecutive Fibonacci numbers. And the 2 consecutive Fibonacci numbers are what's going to allow us to compute the next Fibonacci number, because if we already have 2 consecutive ones, we can compute the next one from them. So how are we going to arrange that? Well, one thing we're going to do is we're going to introduce a new variable, y, and we're going to say something in the variant about y is going to be the Fibonacci of something. At this point, we have 2 choices. Now, if you were not writing this program with an invariant in mind, I bet you would make many mistakes first in being confused about what exactly should y keep track of. You would probably try a few things and notice that it works on some inputs, and then you fix up some initialization and you're going to make many mistakes. If you instead have the invariant in mind, you can make it very clear what your intentions about the loop are, and then you can have a much greater chance of writing the correct program, and maybe even writing it correctly the first time. It seems like we have 2 choices here. One choice would be to make y be the Fibonacci number that, of I minus 1, and the other one is to make y be the Fibonacci of I plus 1. Now, what would happen if we did I minus 1? Well, now we would get some complaints. We're now calling Fibonacci on I minus 1, and the verifier complains that we might not even satisfy the subset constraint of a NAT. In other words, it's saying I minus 1 might be a negative number. And remember, Fibonacci is supposed to be called with non-negative numbers only. So Now we can try to make this loop invariant more complicated to say that, well, if I is equal to 0, then so either I is 0 or this condition holds, and we can make things as complicated as we wish. So instead of doing that, the other solution turns out to lead to a very nice program, just to say that y is the next Fibonacci number. So again, this is the kind of thinking that we're doing before we design the loop. And admittedly, this loop is very simple. It's going to be just 2 lines. But having that clear thinking about what it is that you want your loop to do is going to make you write better loops, loops that are going to be correct more often. So in this case, let's choose x to be the Fibonacci of I and y to be the Fibonacci of I plus 1. So we need to initialize y. So y is going to be initialized to, well, it's going to be the value for 0 plus 1, so the fib of 1. So again, going back to the definition of fib, that means that we should set y to 1. Those are the first 2 Fibonacci numbers, 0 and 1. Okay, we still need to now update x and y to maintain this invariant. So we will have an assignment to x and y, and Daphne allows you to do these assignments in parallel, which is a nice way for some examples. You can write them one after the other as well if you think a little bit more. So what we'd like here is we're going to maintain this invariant. We're just about to increment I, so therefore we'd like to set x to be to make it remain the Fibonacci of I after we increment I. We would like it to be the Fibonacci of I plus 1, and y should then be the Fibonacci of I plus 2. That's what we would like to do to maintain the invariant. Well, we don't want to make use of the fib function like this, but here again the loop invariant comes to our help, because we'd like to have an expression in our program that stands for fib of I plus 1. Now we don't need to think a lot. We can just go up and read what the loop invariant tells us, and lo and behold, it says that we have a variable that is exactly equal to fib of I plus 1. That is the value that we want here to assign to x, so we can just replace this highlighted expression with y, because we know that on entry to the loop, y is equal to fib of I plus 1. Now fib of I plus 2, if we go back to the definition of Fibonacci, we know of course that that is going to be equal to the sum of the 2 previous Fibonacci numbers. So in other words, this is going to be equal to Fibonacci of I plus the Fibonacci of I plus 1. So that's what we'd like to assign to y, but again, we don't want to use the fib function. But luckily, we have an expression that stands exactly for fib of x, for fib of I, which is x. And we have an expression that stands for fib of I plus 1, which is y. And there it is, and Daphne verifies the program for us. So this is how we made use of the invariant. We wrote down a clear description of what we want the loop to do, as if we're writing a specification of the loop. And having that written down and having thought clearly about that, we can now write the loop in the correct way. Just a final note, I did use a parallel assignment here, assigning to x and y. You could try doing this by first assigning to x and then assigning to y, or the other way around. So I encourage you to try that out in the by yourself and see that you can get the program correct in that way as well. Let me now give you an exercise, an assignment to do for yourself. It's going to be similar to the Fibonacci. We're going to write a function that sums the numbers up to and including n. You could do a variation on that. It's typically in computer science that we use half-open intervals, that are intervals that are closed on the low end and open on the upper end. And that typically works very well in many situations. For summation, there the function is often defined to also include that bound n. So it's not the sum of the first n natural numbers, but it's the sum of the numbers up to and including n. You could do a variation of this, but I'll do this one so that you'll see some variation yourself too. Okay, so the sum function is going to be If we're asked for the sum of the numbers up to and including 0, then the answer is 0. Otherwise, it is n plus the sum of the numbers up to and including n plus 1. And the method that you're going to write, let's call it compute sum, it's going to take the bound and it's going to return some integer, natural number in fact. Might as well write that. And the post condition is going to be that that natural number is the output parameter is equal to the sum of the numbers up to and including n. And of course, to write this program, you'll have to write the loop invariant for your loop, because I'd like you to write it with a loop, and then verify the program and make sure that you could try some variations of it yourself to play around with the loop invariants to see what happens if you change certain things, so that you get a good understanding of what loop invariants are. Have fun and program safely.